Hello, and welcome to this introduction to the theory of paracontrolled distributions for singular differential equations. So this is a review talk. It's based on a celebrated paper from 2015 by Gubinelli, Imkeller, and Perkowski, and it also uses some more recent work of Bailleul and Bernicot. Now, word of warning before we get started, I am by no means an expert in this theory. I haven't used it myself so far, although I very much hope to do so in the not too distant future. So I'm not going to give you an expert insider perspective on the theory. What I will do instead is give you something like a Centralblatt or a Matsanet review in video form, given by someone who's not an insider but not a complete outsider either. Now, personally, I do like this kind of review. I find them helpful when they're done genuinely, and I hope that you might find mine helpful in this instance. So, what is the theory about? It's about treating equations that have a singular term. The singular term comes from the interaction between a nonlinearity and a rough driving term. So the equations can be ordinary differential equation, partial differential equation, they can be stochastic, they can be deterministic, but we will look at the simplest case to which the theory applies, which is the case of a first order, nonlinear of course, ordinary differential equation. So here it is, dtu equal f of u times xi. Xi is what I call the rough driver. It's a distribution in C alpha minus 1. That is to say it's the derivative in the sense of distribution of a Euler continuous function of parameter alpha between 0 and 1. Note that we're working on the circle. That's to keep technical difficulties to a minimum and use Fourier series rather than fancier harmonic analysis. But everything works in higher dimensions, it works on RD, it even works on domains of RD or certain Riemannian manifold under appropriate assumptions. But okay, let's keep things simple, work with Fourier series on the circle and have just dtu equal this singular term, which is the product of the nonlinearity with the rough driver. Okay, so the first question we should be asking ourselves is, does this equation even make sense? It's not clear because we have a product here of a distribution in C alpha minus 1 by some function. And what do we know about that function? Well, not very much. I mean, at best, u is going to be C alpha, right? Because let's say if f of u was 1, then dt will be xi. Xi is C alpha minus 1, so u is C alpha. So what we should be assuming on f of u is that it's C alpha. So we're trying to multiply something in C alpha with something in C alpha minus 1. Can we do that? Okay, so if alpha is greater than 1/2, then the answer is yes. We'll see how you do that in a minute. You can always multiply a C alpha distribution by a C beta distribution when alpha plus beta is positive. And alpha plus alpha minus 1 being positive means alpha greater than 1/2. The problem with that for our purpose is that the xi's that we really want to treat are things like the derivative of a typical trajectory of the Brownian motion. And a typical trajectory of the Brownian motion is Euler regular, but only of parameter alpha strictly smaller than 1/2. So the threshold here is problematic. For the applications we have in mind, the general theory of product of distribution in C alpha classes for alpha and R is not enough. That's where paracontrolled distribution theory comes in. The theory will allow us to make sense of this particular product when alpha is just greater than 1/3. So we are below the 1/2 threshold and we can treat the typical trajectories of the Brownian motion that we care about. But we don't do that by having a theory of general multiplications of a C alpha by a C alpha minus 1 function for alpha between 1/3 and 1/2. What we do is we look at this particular product. So we use the equation, we use the fact that f of u and xi are very much linked to each other. And not only that, but we will need some extra information on the xi. So we'll see how that's done. But once this is done, we have an equation that makes sense, but we don't just want an equation that makes sense, we would like to solve it. So what we need to solve are estimates. We need to know how the solution u depends on the driver xi in such a way that we could approximate the right-hand side by something smoother, get some approximate solutions, show that the approximate solutions converge to something, and then have that something be the solution of our original problem. So we will do that. We will not only make sense of the product, but we will do so in such a way that produces a priori estimates. So these are the a priori estimates that we will get. We will be able to control the C alpha norm of the solution in terms of a smooth function of the initial data, which in that case is just an element of R, the C alpha minus 1 norm of the driver, that's to be expected, but also the C2 alpha minus 1 norm of some objects related to the driver, some sort of enhanced version of it, which is maybe a little bit less expected unless you have some knowledge of, say, rough path theory, in which case you would exactly expect that. Now, staring at this a priori estimate, let me make two very hand-wavy remarks at this stage. One is that what we have here is really an instance of the regularity structure philosophy. So we look at the regularity of the solution in terms of basic building blocks, which are not your usual, say, polynomials, but they are built on the rough driver. So we have some first order approximation using this term and second order approximation using this term. And now the fact that we need two level of approximation to solve a first order differential equation, that might look funny at first, just coming from smooth calculus, but it's not if you've done something like Ito calculus, for instance, where you expect a second order correction even for first order problem. And one way to think about this is that this is tied up with the 1/2 threshold. If you have objects that are typically C1/2, that means that they scale as a square root of the length of an interval. So their second order approximation scale linearly with the length of the interval. So they correspond to something like dt in smooth calculus. So the fact that we have this extra term, this extra information on psi, this is to be expected due to the roughness of the problem. And this is very similar to the second order correction term that you see in something like Ito formula. And we'll see a lot more of this analogy at the end of the talk. Now, if you don't know any of this, rough path, Ito integration, that doesn't really matter because most of the talk will really be just basic harmonic analysis with Fourier series. And let's start doing that now. Indeed, at the heart of paracontrolled distribution theory, what you find is Littlewood-Paley theory. Now, Littlewood-Paley theory, let me remind you what that is. This is a form of harmonic analysis that's very useful in the study of differential equations, and it consists in decomposing function using these kinds of projectors, which in the context of Fourier series are just the following. They take a Fourier series, these are the Fourier coefficients, these are the elements of the Fourier basis, and it restricts it to those frequencies that are roughly of the size 2 to the j. Now, these Littlewood-Paley projectors obviously give you an orthogonal decomposition of L2 because the trigonometric basis itself is an orthonormal basis. So you have this characterization of the L2 norm using Littlewood-Paley projectors. But more interestingly, you can use Littlewood-Paley projectors to characterize the norms of all sorts of other function spaces. For instance, if you look at LP, P in the reflexive range, what you can do is form a square function out of your Littlewood-Paley pieces and take the LP norm of that. And that would give you an equivalent norm, so equivalent up to constant, to the original LP norm. That tells you that decomposing a Fourier series into dyadic block gives you an unconditional decomposition of LP. And that's very helpful in studying the boundedness of operators on LP spaces. Now, more to the point of this talk, this allows you to characterize C alpha spaces, and the characterization of C alpha spaces using Littlewood-Paley projectors is the following. You take the Littlewood-Paley blocks, take their sup norms, and then multiply them by a weight 2 to the j alpha. Now, for the sake of this talk, you can think of that for any alpha in R as being the definition of C alpha. It's a little cheat compared to the standard spaces, but pretty minimal. Now, building on Littlewood-Paley theory, we have paradifferential calculus. That's a toolkit that was introduced by Jean-Michel Bonny back in 1981, and that has proven extremely useful in the analysis of nonlinear partial differential equation. So the idea is to decompose the functions into their Littlewood-Paley expansion and use that to study things like products. So if I have a product of two functions, like here, f and g, I can decompose f into its Littlewood-Paley decomposition and g into this Littlewood-Paley decomposition. And then I have this double sum, and I can separate it into three pieces. The piece where the k is substantially smaller than the j, the piece where the j is substantially smaller than the k, and the piece where the j and the k are roughly the same. So, here in G we only have substantially lower frequencies, and here in G we have substantially higher frequencies than for F, and here we have the same. So we get three terms that we call the paraproducts of f by g, g by f, and here we have something that we call the resonant product, right? So these are paraproducts, and I'm going to call that the resonant product. Now the point of doing this decomposition is that the paraproduct terms are typically easier to study, and the difficulty then gets shifted from the full product to just the resonant product. We see that, for instance, in this lemma of Bonny that we're going to prove in a second, that tells us that if you take a paraproduct of a C alpha distribution by a C beta distribution, and just to be in the non-trivial case, let's assume that alpha is negative, then you get something in C alpha plus beta, and with an estimate, as you guess, by the product of the C alpha norm of f times the C beta norm of g. Now the same is going to be true for the resonant product, except we're going to pick up this condition alpha plus beta greater than 0. And remember that this is this condition that prevents us from multiplying f of u that's in C alpha by xi that's in C alpha minus 1 when alpha is smaller than 1/2. So this is where the difficulty lies. And in extending the product such that we can treat f of u times xi below the regularity threshold alpha equal 1/2, all our attention will be focused on the resonant part of the product. So I'm going to prove this lemma right now, at least sketch the proof, because it really contains the essential ideas of paradifferential calculus that you see in all of the other results that I will mention later. Okay, so we need to have a look at the paraproduct and the resonant product. And if I look at the terms inside those sums, what we can first notice is that they are localized in frequencies. Now, where are they localized? If I apply delta L to delta K, delta J, G times the sum of the delta KF, K equal minus 1 to J minus 2, then I claim that this is non-zero only when L is close to J. And the reason for that is because when I multiply two elements of the Fourier basis, En times En, I get En plus M, and if N is roughly 2 to the J and M is roughly 2 to the K, with K smaller than J minus 2, then I get that N plus M is going to be, at least 2J minus 2J minus 2, and at most 2J plus 1 plus 2J minus 1. And these two quantities here are again roughly 2 to the J. Now it's different with the resonant product, and it's harder to treat the resonant product precisely because I don't have as much information on the frequency localization of the terms in the sum, because this is going to be non-zero this time only when L is not too large compared to J. So L smaller than J plus 1. The reason for that now is because if you do the same reasoning as here, you only get that N plus M is greater than, say, 2J minus 2J, which is just 0, but still smaller than 2J plus 1 times 2, so 2J plus 2. Here, in the paraproduct case, we have terms that are localized roughly on the same dyadic annulus, plus or minus 1, as G, whereas with the resonant product, all we can say is that these terms are in the union of the annuli up to the annuli J plus 1. Okay, now that we have this frequency localization, we can start computing the C alpha plus beta norms. So let's have a look at them. Let's do the sup of delta L pi f G in sup norm times the weight 2L alpha plus beta. Right, now what is that? This is the sup, the weight, and then here we have a sum, but it's really just a finite sum of the j's that are close enough to L, times the sum k equal minus 1 to j minus 2, delta kf, delta j g. Alright, so now up to a constant, we can pull out from here, L is roughly j, the C beta norm of g, and then we are left with the sup L greater than minus 1 of 2L alpha times the sum k equal 1 to L minus 2 of the sup norm of the delta kf. And that is controlled by the C alpha norm of f times the C beta norm of G times the supremum of 2L alpha times the sum k equal minus 1 to L minus 2 of 2 to the minus k alpha. And this here is just a finite constant because my alpha is smaller than 0 by assumption. So that's the way you handle the power product term, and it's quite easy because the sum in J collapses to just a sum of a couple of terms. Okay, so let's do the resonant term now. So we need to control supremum of L, 2L alpha plus beta, delta L of F resonant product G in sup norm. Now, this is a sum in J, but the sum in J will start at L minus 1. So this is smaller than supremum of L, 2L alpha plus beta times the sum J equal L minus 1 to infinity of delta L of delta J of F infinity delta J of G infinity. And now you can control that by the C alpha norm of F times the C beta norm of G, and what you hope is going to be a constant is the supremum L greater than minus 1 of the sum starting at L minus 1 to infinity of 2 minus J minus L times alpha plus beta. And now this is a geometric series. This is going to be finite provided alpha plus beta is positive. And that's exactly where we pick up this condition. So we have seen that paradifferential calculus is very good at estimating products in various function spaces. But the other thing it's useful for is simplifying nonlinearities through a procedure called paralinerisation. Now here is a paralinerisation result. What it tells us is that a nonlinearity f of u is pretty close to being a paraproduct of u by f prime u. Now the only difference is going to be a term fu sharp which is smoother than the original u. It's in C2 alpha. Now the usefulness of that paralinerisation technique, we'll see that on the next slide, but that's clear to imagine. It's that if you're going to do a complicated operation like taking a resonant product on f of u, really all you have to do is do it on u and then take the power product, which is not too hard. And then you're going to have to do this more complicated operation on a term fu sharp, which is much smoother than what you started from. And we'll see that for the operation of taking the resonant product with psi, doing it on the sharp term will be easy, and so we fundamentally would have reduced the problem from doing it on f of u to doing it on u. Now let me give you a quick idea about how the proof goes. So you write f of u sharp as a sum of these terms, and then you remember from the proof we've seen before that the terms in the power product are going to be frequency localized, and they're going to be frequency localized almost on the same annulus as the terms here, plus or minus 1 annulus. So what you have in fu sharp is a sum of terms which are well localized in frequency. Now these terms, they're obtained by applying these operators, and these operators are convolution operators. You can compute explicitly their kernels. So you can write epsilon j as a convolution operator, and then you can exploit some fundamental properties of these kernels. The kernels here that comes from the delta j's have mean 0, and the kernels that come from the sum of the delta k will have integral 1. Now what this allows you to do is to add terms like this one or this one for free because you're integrating them against kjxy, which has mean 0. So what you've done in effect is write things as a certain integral operator with this kernel, and here what we have is a first order Taylor expansion of f. Okay, so now to get an estimate, you have this first order Taylor expansion. So you estimate using the sup norm of the second derivative of f, you pick up the C alpha norm of u square, and then you have a term here that scales like y minus z to the 2 alpha. And so y minus z to the 2 alpha, if you combine that with the scaling property of the kj, will tell you that the sup norm of the epsilon j scales like 2 to the minus 2 alpha j. But now your epsilon j's are frequency localized, they scale in that particular way. This is exactly telling you that fu sharp is in C2 alpha. So let us have a look at what happens when we apply this paralinerisation technique to the nonlinearity resonant product with the driver psi. So we paralinerise f of u, we get f of u sharp plus a power product. And the idea is that this is going to be pretty close to the standard product of f prime u with the resonant product of u and psi. And why is that? Because when you look at the difference, well, you pick up the sharp term, resonant product with psi, and then you pick up this difference between the power product, resonant product with psi, and the actual multiplication with the resonant product of u and psi. And this difference here is a familiar term in paradifferential calculus. It's what we call the corrector, which is a trilinear form that we apply here to the terms f prime u, u, and psi. And the sum of these two terms, the corrector and the sharp term, resonant product psi, we will denote by pi subscript f of u psi. Now, why is that good? Because we have good estimates on correctors. Indeed, the corrector is bounded from C alpha cross C beta cross C gamma into C alpha plus beta plus gamma whenever alpha plus beta plus gamma is greater than 0. And that's a theorem you prove in a similar way than the theorem we've proven before. It's a bit more technical, but it's the same sort of ideas. Now, why is that helpful for us? Well, remember, this is in C alpha, this is in C alpha, this is in C alpha minus 1. When you sum these things, you get 3 alpha minus 1, and that is positive whenever alpha is greater than 1/3. And so you're left with this term here, but this term here, this is C2 alpha, and this is C alpha minus 1. Again, the resonant product will make sense whenever alpha is greater than 1/3. So what we have now is that the difference between the resonant product of f of u and psi and this product times the resonant product is in C3 alpha minus 1. So all of that makes sense and can be well estimated whenever alpha is greater than 1/3. So we've really reduced the problem to understanding the behavior not of f of u resonant product with psi, but just u resonant product with psi. And we need to estimate that. Now the next step in that paralinerization philosophy is to introduce the solution to the linear equation dt theta equal to psi, and then compare u to a prior product that doesn't just involve u, but involve theta. And what we will see is that the difference between u and this prior product is a term which once again is smoother than u itself. So what this does is reduce the problem even one step further. We've reduced the study of f of u resonant product psi to the study of just u resonant product psi, and now we're going to reduce it to the study of theta resonant product psi. So here is how it works. You look at the resonant product of u and psi, you use this formula, you pick up the resonant product of u theta sharp with psi, which should be fine as long as we can prove that this is indeed in C2 alpha, and then we have the resonant product of the power product with psi, which is basically a standard product of f of u with theta resonant product psi, except for corrector term. But we're not worried about corrector terms because those ones are fine. This is in C alpha, this is in C alpha because of this equation, and this is in C alpha minus 1. So for alpha greater than 1/3, this corrector term is going to be just fine. Now this term will be fine as long as we can show that u theta sharp is in C2 alpha, and then we are left with that term that involves the resonant product of theta with psi rather than u with psi. Now, in order to treat this term, what we need to know about theta resonant product psi is that it's C2 alpha minus 1. And that is not something we're going to be able to deduce. This is something we're going to have to assume. Now, notice that we're assuming something about the driver itself, right? This has nothing to do with the equation. Theta is like an antiderivative of the driver. The driver is in C alpha minus 1. We hope that theta will be in C alpha and that the resonant product will be indeed in C2 alpha minus 1. But that's an assumption we make here. In practice, you would use the specific nature of your driver to prove this assumption. So typically, if you're looking at a stochastic problem and you have something like derivative of trajectories of the Brownian, you will use the nature of the Brownian motion to prove that this holds for all alpha strictly smaller than 1/2. But for us, this is an assumption about the nature of the driver. And having that assumption, we get that this term is in C2 alpha minus 1, this term is in C alpha, therefore this product is in C3 alpha minus 1 for alpha greater than 1/3. And we're left with this term, and again we need to show that the regularized version U theta sharp is in C2 alpha. So what we have to show now is that U theta sharp is in C2 alpha, and we want a control of that by some smooth function of the C alpha minus 1 norm of psi and the C2 alpha minus 1 norm of theta resonant product with psi. The way you do that is by using the equation for the derivative of that U theta sharp, and then you get the 6 terms and you start looking at the regularity of all 6 terms. So here we have something C alpha, and then C2 alpha minus 1, so that gives us in C4 alpha minus 1. Here we have alpha minus 1 plus alpha, that's 2 alpha minus 1. Here we have alpha minus 1 plus alpha, that's 2 alpha minus 1. Here we have 3 alpha minus 1 plus alpha, that's 4 alpha minus 1. And here we have 2 alpha minus 1, 3 alpha minus 1, 4 alpha minus 1, and here we have 3 alpha minus 1. Now, there's a bit more work from that because we're assuming a priori that this is in C2 alpha, so you get an implicit equation, you have to make a constant smaller than 1, use some localization, so there's some more work to be done, but eventually from this equation and all the knowledge we have before, we get to this a priori estimate. So going back to our first slide, I hope that what we've done so far allows you to understand how we make sense of this equation when alpha is greater than 1/3, using all sorts of power products and paralinerisation techniques to decompose this into objects that do make sense, and how we get a priori estimates of that form. Now, I haven't really talked about the initial data. You would have to subtract it and then check how everything depends on it, but that's not particularly difficult. The key thing to remember is that the a priori estimates that we get and the information that we need about the driver to do all of this is not just that the driver is in C alpha minus 1, but that the term theta resonant product with the driver is in C2 alpha minus 1. Now, I'd like to finish with the following question. Is paradifferential calculus natural in the context of singular differential equation, or is it just a nice set of tricks that one can use? Well, if you come from harmonic analysis, the answer is, well, it's obviously natural because you're dealing with products, so power products allow you to decompose them and find where the difficulty really is, and paralinerisation allow you to simplify the nonlinearity and further narrow down the problem such that you pick up what exactly is the difficulty. And we've done that, and we've seen that the difficulty really lies in the term theta resonant product with psi. Now, this is very natural to a harmonic analyst, but if you don't come from harmonic analysis, maybe you would prefer some alternative approaches. For instance, you could take a rough pass approach to problems like the one we've seen today, and then instead of having the extra information on the driver being given by theta resonant product psi, the extra information will be given by an iterated integral of psi. Now, if you know regularity structures more generally, maybe for the specific equation you're looking at, there might be a specific regularity structure that is even more natural. And by using regularity structures, you would pick not just a technique to make sense of the equation and solve it, but also a way to understand all of the possible solutions depending on how you approximate the solutions. So this is very powerful and very natural and probably closer to standard calculus than what we've seen today. But I would like to finish with an analogy between paradifferential calculus and Ito calculus. And to me, this shows how natural disharmonic analysis ideas are and how you can transfer ID between stochastic and harmonic analysis. So here's the first one of those analogies. On the left-hand side, we have the decomposition of a product into power product plus a resonant term. On the right-hand side, we have the analog of the Leibniz rule for products of stochastic processes. And what we get is not quite what you would expect from Leibniz rule. It has an extra term that comes from the fact that, well, these are stochastic processes and they have a non-trivial covariation. Now, these two things are very similar because if you think of the construction of the integral y dx in Ito calculus, because you need the process to be adapted, what you have is that y will be on a time interval before the increment of x. Just like here, the g would have frequencies lower than the frequencies of f. And the covariance term happens when you look at the same time interval, or here the resonant term happen when you look at the same dyadic analysis in the lithoid Pele decomposition. A second analogy, the celebrated Ito formula here. Now, in Ito calculus, when you try to integrate against a function of your base stochastic process, it's not the same thing as integrating against f prime x dx. There is a correction term involving the second derivative of f and the quadratic variation process of x. Now, this is similar to the paralinerisation formula in paradifferential calculus, where when you look at a function of your base function little f, you get a power product, and the power product involves f prime f being lower in frequency than little f. That's similar to here, the f prime capital X, when you think of the discretization of the integral, leaving on a time interval on the left-hand side of the increment of x. And then you have the sharp term here. Okay, this is not quite as neat as here as a formula and an equality just involving the second derivative, but the scales like the sup norm of the second derivative of capital F. Now, for the last analogy, we have on the right a celebrated formula again in Ito calculus that involves three processes, x, y, and z, and look at a compensation between this bracket and this expression here. And the analog of that in paradifferential calculus is the compensation between this term and that term. We've seen that the difference between these two terms is exactly what we call the corrector. And the corrector, fair enough, is not zero. That's not as neat as in Ito calculus, but it is smoother than these two terms. So it picks up the cancellation between the two, just like this formula picks up a perfect cancellation between this term and that term. Okay, so I hope you've enjoyed this analogy just as much as I did when I first read about them in a paper of Bailleul and Bernicot, and more generally that this talk has helped you understand how paradifferential calculus and lithoid Pele theory more generally helps in studying singular and stochastic differential equations. Now, to finish, I'd like to mention that there has been a lot of exciting work in the field in the last couple of years. The work of Bailleul and Bernicot that I mentioned allows you to do higher order para-controlled distribution theory. It also allows you to adapt the lithoid Pele decomposition to an operator and therefore treat problems on domain or certain Riemannian manifolds or complex equation with coefficients. Now, beyond that, there's also the work of Perkowski that I'd like to mention that shows that the gap between regularity structure theory and paracontrolled distribution theory is even smaller than one would have imagined at the beginning. So these are great papers to read, and I'm going to stop here. Many thanks for your attention.